All right, let's learn something about normal random variables. This is problem number 17, and it is quite a bit more challenging, or at least more unfamiliar than anything that's come so far. So we've got some properties here. One, if you take a normal random variable and you multiply it by some scalar, all that does is scale up the mean and the standard deviation, and you still have a normal distribution. And then if you have independent normal random variables and you add them together, you will get another normal random variable. And the way you get the mean of that new normal and the standard deviation of that new normal comes from these two statements right here. So in this problem, we've got we're given standard deviations. So I'm gonna take the information from the problem. I'm gonna write a new statement here based on this and kind of walk you through it. So we've got a normal random variable with mean 0 and standard deviation 0.0056. And we've got another normal random variable, again with mean 0, but this one with standard deviation 0.0044. And there is an h tacked on the end right there. Do that correctly. And here. And then we want the average of those two. So basically what we want to do is multiply both of those normal random variables by 1/2 or divide the entire construction by 2. It's the same. And that is going to equal some other normal random variable. So let's kind of simplify, starting with the mean. According to this rule, our new mean of the normal variable is just going to be the sum of these, and then according to this rule, times the scalar. So the scalar of 1/2. So 0 plus 0 times 1/2 is just 0. So the mean of our normal random variable, the new one, is just 0. But of course, this problem isn't about the mean, it's about the standard error, and that's what makes it challenging. And notice that this statement is that the sum of the variances is equal to the new variance, not the sum of the standard deviations. So I'm going to pull this down here and just do a little bit of work on it. So we've got the normal, and let's go ahead and just write it out. 0.0056h over 2. I think this is going to make it a little bit more easy to understand. Again, 0.0044 over 2. So I just scaled it up. Now I'm going to take these two standard errors and I'm going to apply this formula right here. So one, how do you convert the standard error to variance? You square it. So we have 0.0056h over 2 squared, just applying this rule right here, squaring my first standard error, plus 0.0044h over 2 squared. The sum of those two is going to equal the variance of our new normal. So let's kind of condense that together. We have 0.0056 squared times h squared plus 0.0044 squared times h squared, and all of that is going to be over 4, right? Because we square the denominator along with the numerator, and then we have a common denominator. So if you're looking at the answer key and racking your brain trying to figure out why is there a 4 when I'm just averaging, well, this is the reason. It's because we're summing the variances in order to make our way to the standard error. And then from here, it's kind of just straightforward math, right? We can create a single term on top and divide that term by 4 if we want. So when you sum 0.0056 squared and 0.0044 squared and then divide by 4, what you get is 0.00001268 h squared. So this is the variance of our new normal, but we don't want the variance, we want the standard error. So we're going to take the square root of that value, and that is going to give us 0.00356 and some dust there on the end, h. So you square root here, get the standard error there, and now we can apply our z-score. We have a mean, 0, we have a standard error here of 0.00356h, and then this x, we're asked to find if this measurement error, the average of this measurement error is within 0.005h. So to find our z-score, we're going to let that 0.005h be our x. We're going to subtract off the mean of 0, and then we're going to divide by the standard error. And this is really, we have two possibilities, both positive and negative there, because it's within that range. All right, so the math comes out very easily here. Minus 0 does nothing, so really, and the h's are going to cancel. So really what you have is 0.005 divided by 0.00356, which is plus or minus 1.40, and maybe you could round that to a 5 on the end there. That's your z-score. So you're going to go over to your standard normal table, and you're going to find your values for your z-score, and I'll just kind of sketch it out here. It is about 0.92, or if you're on the negative side, it is about 0.08. The distribution is symmetric, which does make this part of the problem pretty easy. Basically what we're saying here, this is about 0.08, and this is about 0.92. So we want to know, is the standard error going to be somewhere within this part of the curve? Is it going to fall between these two values? So it's just going to be 1 minus the same area over here on both sides. So 1 minus 0.08 from over here minus the 0.08 from over here. That is, there's 0.08 area in there, and that is 0.84. So a lot going on in this problem, but it's a really good problem, because if you can come to a place where you understand all of the pieces, you're actually going to be head and shoulders above a lot of people that are going through with these exams. The normal random variable, and specifically the properties of an independent normal random variable, are all over exam P. And then again, when you get to Mass 1, there's the whole lot of the exam is dedicated to your understanding of independent normal random variables, this rule of their variances and their means, how to use these scores. So very important problem. This one is really worth thinking about for 30 minutes or several days in a row, however long it takes to get to the place where you fully understand every single piece of it. If you just kind of rush through and go, oh, well, this one's difficult, but I can do the next one, you're really going to miss out on some very valuable information and a skill that'll kind of set you apart and make the exam feel a lot easier.